Hello everyone, welcome back to our channel. Dear aspirants, let's discuss the next topic, that is first order and non-first order NMR. Okay, so here we have some conditions. Whatever the proton NMR spectra which we are having for a particular chemical compound, we need to identify whether the given NMR spectra is first order or second order. What are the conditions? The first and very important condition is delta mu by J is greater than 6. The delta mu is the chemical shift in edges. What is the definition of chemical shift in edges? The difference between the precessional frequencies of the sample protons and reference protons is commonly called as chemical shift in edges. That is delta mu. J, we know that this is coupling constant, the distance between any lines in the NMR signal, that is coupling constant. So what will be the condition? Delta mu by J is greater than 6, then the spectra is called as first order spectra. If it is less than 6, that is non first order spectra or second order spectra. How the first order spectra will be appeared? It is in simple form. The non first order spectra is complex form. The first order spectra follows n plus 1 rule. Multiplicity we have discussed, right? The number of lines in a proton NMR signal is commonly called as multiplicity. So multiplicity can be calculated by using n plus 1 rule. So first order spectra follows n plus 1 rule. The non first order spectra will not obey n plus 1 rule. Right? In order to identify the different peaks, singlet, doublet, triplet, quartet, pentet, sextet, like that we are following generally Pascal triangle or not. The first order spectra follows Pascal triangle intensity ratio. It will not follow Pascal triangle, non-first order spectra. In case of the first order spectra, what we are observing, the distance between the signals are higher. It means the separation is good. Because of the more separation, we can easily extract the information of chemical shift values and coupling constant values as far as first order spectra is concerned. But in case of non-first order spectra, what happens? The signals are become very close. Because of that reason, we could not be able to easily extract the delta chemical shift values and the coupling constant values of the protons in case of non-first order spectra. Okay, here is the example. Delta mu is chemical shift difference in edges. J is coupling constant. Assume that we have one hypothetical molecule, the same hypothetical molecule we're taking here also. Two protons are there, HA and HB. Right? Coupling constant means distance between these two lines or the distance between these two lines. So these two protons are adjacent to each other. That's why the coupling constant is same. Already we know that coupling constant values are useful to find out the adjacent protons present in the chemical molecule, right? Whenever the J value is same means what? The protons are adjacent to each other. Okay. So assume that the precessional frequency of Hb proton is 100 Hz. The precessional frequency of Ha is 80. Right? So calculate delta mu by J. 100 minus 80, that is equal to 20. So coupling constant is 2. 20 by 2 equal to 10. So delta mu by J is greater than or equal to 6 or not. That's why the spectra is commonly called as a first order spectrum. Okay, if you see this one, second case, 90, 85, the J value is same. So delta mu equal to 5 and 5 by 2 equal to 2.5, that is non-first order spectrum. So in this case, what we are happening? 90, this is 85. The difference is only 5, but here the difference is what? Higher or not? It means if the separation is good, that is simply first order spectra. If the separation is not good, that is non-first order spectra. So in this way you need to remember. With increasing in the field strength, the signals comes close, merges will each other, complexity increases, first order becomes non first order spectra. So what we are observing, already we know that precisional frequencies are directly proportional to the chemical shift, right? This is in turn proportional to the strength of the external magnetic field. Already we know that if we increase the strength of the external magnetic field, precisional frequency increases, thereby chemical shift value increases. So if you decrease the field strength, what happens? Precisional frequency decreases, thereby chemical shift values decreases. What the people are saying, whenever you decrease the strength of the external magnetic field, what happens? The separation between the signals will become decreases. The separation decreases means what happens? The signals are going to be merged. See this one. If he is 200 megahertz field strength, so the separation is good. This is 10 more than 6. This is 8 more than 6. This is 5 less than 6. This is 3 less than 6. What is happening? From top to bottom, the distance between the signals are decreasing. Thereby the lines are becoming closer or not. So whenever we decrease like this, what happens? Whatever the center lines we have, the center lines intensity will be increased and the outer lines intensity will be decreased. So in case of any complex spectra, what we will observe, the center peaks with the highest intensity, the left and right peaks are with the lower intensity. See, okay, so in this way the first order spectra is converted into second order spectra. So if you want to convert the non first order spectra into first order spectra, what should we do? We need to move in this way or not? Previously what we have done, we have decreased the strength of external magnetic field. Now what we have to do, we have to increase the strength of the external magnetic field. So if we increase the strength of the external magnetic field, the complex spectra will be converted into simple spectra. The non first order spectra will be converted into first order spectra. Okay, so let's see some of the notations which we need to use in case of the first order and the non first order NMR spectra. Okay, first order NMR notation. Suppose the first condition, if the molecule contains only one set of protons, already we know that how to identify chemically equivalent and non-equivalent sets of protons. Already we had a clear discussion in the first video. So we can easily identify how many types of different kinds of protons which are available in the different chemical molecules. So sometimes the first case is what? If the system containing only one set of protons. For that, how can we represent? The representation is like that. We need to select the letter A, right? If you have more than one proton, the number is represented with small a in the suffix. Okay, you can say subscript also. The number of protons corresponding to the set. If you take this molecule CH4, first molecule. So how many hydrogens are there? 4 hydrogens are not. Right? How many sets of protons are there? Only one set is not. That's why it is represented what? A4. Suppose if you take this one, all are same kind of protons. How many? 6 protons. That's why A6. Here also, these 6 protons are same or not? So represented as 6. Okay. If you see these 4 protons, chemically equivalent or not? One set or not? That's why it is represented as what? A4. I think you understand very well. Okay. This is the first kind of notation. In case of this one, see 9 protons, A9, cyclobutane A8, hexane A12. In that way we can observe. In this case 1 2 3 4 5 6 7 8. In this case how many total? 3 plus 3 6, 6 plus 3 9, 9 plus 9 18, A18. The second condition is that if the molecule is having two non-equivalent sets of protons. So what are the letters which we are using? A and X. Generally, what these people are following the letters A, B, C, D. Right? If you see the distance between A and X, it's a longer distance or not. So what the people are identifying, whenever the chemical shift values of the non-equivalent sets of protons are having a higher difference, then we can use the terminology called as capital A and capital X. If A type is there, AA. If X type is there, XX. Take one example, CH3, CH2, Cl. Okay, because of the more influence of the chlorine on the first carbon, these protons chemical shift values are higher because of more electronegativity. These protons chemical shift values are lesser. See, this is 3.4 and this is 1.4. So the difference between these two chemical shift values are higher or not. That's why one will be considered as A type category, another will be considered as X type category. Okay, so here we have flexibility, which one will be considered as A type and which one will be considered as X type. Here there is no restriction to give the letters. That is according to your wish. If you want to give X to these protons, you can give. If you want to give A to this one, you can give. So there is no restriction. So it becomes what? If you consider this is X type, how many? 3. So X3. If you consider this one is A, how many protons are there? 2. So A2X3 system. Suppose if you take this one as A3. If you take this one as X, X2. So in this way you can identify the system AX. AX is simply what? The chemical shift values difference between the protons are higher. Okay. So here we have different skeletons. See this. Assume that this is A type proton and this one is B type proton. You have two types of protons, A type, and every time we need to identify non-equivalent sets of protons only. This notation is only to identify the non-equivalent sets of protons. It means here you have some different groups. So only two protons are there, A type and B type. So A type is considered with the notation A, B type is considered with the notation X. The chemical shift values difference between these two protons are higher, that's why it is AX. So A will give the doublet to B proton, B will give the doublet to A proton. That's why it is considered as doublet. Doublet means how many signals? Two signals, two doublet means the number of lines will become how many? 4. Similarly, if you consider it is A type, then it will become what? X type. So two protons are there. So AX2 or A2X. You have the flexibility, right? So doublet by triplet. Doublet mean 2, triplet mean 3. So 3 plus 2 equal to 5. Similarly, this is A type, this is X type. AX3 or A3X. Okay. Here you can write for the convenience, this one is also X type category. Okay. AX. A2X3. In this way, we can have different kinds of the lines in the signals. So take this example, CH2, CH2. These two are not equivalent. These two are chemically non-equivalent. That's why one is considered as A type, another one is considered as X type. So A2X2. Okay. In this case, A2X3 or A2X3. In this way, we can give the notation in case of the first order spectrum. So if the molecule containing three non-equivalent sets of protons, what should we do? We need to give three letters. A, M, X. If you see the letters, A is the first, X is the last, M is somewhere between A and X or not in the series. That's why we are going to consider AMX. The notation is AAMMXX. Generally, these kind of protons are observed in what? Only ring protons are following the AMX pattern in most of the cases. Okay, if you see this example, see this aldehyde proton is chemically non-equivalent. There is no relation. It will give a separate signal. But if you consider the ring, you have three different protons, right? These three are chemically non-equivalent. That's why these three protons will be considered in the system called as a AMX system. The people will ask you, what is the notation for the first order spectra? A type, AX type, AMX type. Three type is there. AMX type is very important. The people will ask you related to this one. You can say simply this kind of system is identified by the ring protons. Okay. Sometimes in olefins also we can observe. See, these three are chemically non-equivalent. If you see the chemical shift value difference, that's not larger. Okay, because of that reason, one will be considered as A type, another will be considered as M type, and another will be considered as X type. So in all the cases, we can observe. In styrene also, we can observe the situation. See this. In styrene oxide also, we can observe the situation. Already we know that whenever you have some group here, these two will be chemically non-equivalent. Okay, so in such type of cases, in AMX system, what happens? We cannot follow n plus 1 rule directly. We can follow stepwise n plus 1 rule. This is very, very important rule. This model is commonly called as a tree model for the spreading of the signal. How can we identify the signals depending upon the stepwise n plus 1 rule? It's very, very important. You need to remember. In case of the AMX system, we are going to observe only stepwise n plus 1 rule. Okay, let us see how can we identify. See this one. This is one example. Styrene oxide. In the styrene oxide, we are not talking about the benzene protons. Remember that, right? Our concern is what? These three protons, ring protons. See, the chemical shift value is 2.8, 3.2, and 3.9. Okay, if you see, the difference is not larger. If you see, the difference is not larger. That's why we have given A, M, and X. So what is the splitting pattern in such type of cases? That is very much important. Okay, so how we are going to have the splitting pattern? See this one. First, take HA couple with HM, and HA couple with HX. Two possibilities are there, right? So HA couple with HM, you will get doublet or not? Okay, according to n plus 1 rule. So here we are following stepwise n plus 1 rule. In the first case, what we are observing, the HA proton will couple with the HM proton. According to n plus 1 rule, what happens? 1 plus 1. So, two lines we will get or not? So, the HA is going to get a doublet because of the HM. So, that is representation. The HA is coupling with the HM to produce doublet. This is one line. This is one line. Doublet. Now, what happens? The HA is going to couple with HX. So, HX will give another doublet. Already one doublet is there, two lines are already appeared in the spectra. That's why what happens, whatever the doublet which we are getting from the HX to HA, that can be split into two. One with the first doublet coming from the HM coupling. So this doublet is again is going to give two signal. The second doublet is going to give two signals. So for HA, how many lines are appeared? Four lines are appeared. Clear? Similarly, HX initially coupled with HM, we will get doublet. This is one line, this is another line. Then HX will couple with HA. HA will give the doublet. So this is one doublet and this is one doublet. Similarly, HM will couple with the HX, then doublet is there. Then HM will couple with the HA. Again, two doublets are there. So finally, we are going to get doublet by doublet for HA proton, that is 4 lines. Again, doublet by doublet for HX proton, doublet by doublet for HM proton. So finally, we are getting how many lines in the spectra? 4 plus 4 plus 4. So 12 lines we will obtain in the spectra. So this is because of what? Stepwise n plus 1. So here one time we used n plus 1. Here we used 1 plus 1. Again we used n plus 1. This is commonly called as stepwise n plus 1. So in case of the ring protons, we are going to identify the AMX system. In the AMX system, we are observing stepwise n plus 1. Very important. In every interview, the people will ask you, give me one example to AMX system and why. Take simply styrene oxide and explain everything. Right? So for your understanding, here some more examples are there. Right? According to these examples, so you can have the lines. Right? In generally, we are going to get 12 lines for the ring protons. Okay, with different coupling strengths. So this is all about the notation of first order spectra. Let's see the notation for non-first order spectra. So what is the condition for non-first order spectra? Delta mu by J is less than or equal to 6. The chemical shift values are closer. That's why the spectra is very complex in nature. So chemical shift values are closer. That's why what we are taking the first one. If the molecules are having two non-equivalent sets of protons. So two non-equivalent means we need to give two letters. What are the letters? A and B. The difference between should be the protons are going to be very less. So if you see in series of ABCD, so A and B side by side, na? That's why the people are considering AB. If the molecule is having three non-equivalent sets of protons, consider ABC. So in case of ABC system, the examples are same. Whatever the examples which we have taken in the AMX system, the same examples we are going to take in the ABC system also, but there we have used high frequency instrument. Here we are using low frequency instrument. Assume that in case of the AMX system you have used 500 megahertz instrument. Here you will use 60 megahertz instrument. The 60 megahertz instrument cannot be recognized all these kind of protons in an efficient manner. That's why simply you can say the low frequency instruments we can use ABC. In a high frequency instrument we can use AMX system. Right? First one is AB system, second one is ABC system, third one is ABX system. In this case what happens? The first two chemical shift values are closer. The third proton chemical shift value is large. So we have three non-equivalent sets of protons in which two non-equivalent sets of protons chemical shift values are closer. The third pattern is going to be higher. Right? This is all about the first order and the non-first order NMR spectra. Okay, so in the next video, we will be discussing about how can we simplify the non-first order spectra. Non-first order spectra means it is a complex spectra or not. So how can we convert the complex spectra into simple spectra? What are the methods which are available to convert the complex spectra into simple spectra? That will be discussed in the next video. Okay, thank you.